Hello, this is Mrs. Tempest, and today we're going to be talking about chemical reactions, properties, and changes. So in previous units, you learned that physical properties are characteristics of a substance that can be observed or measured without changing the composition. Some examples include color, melting point, boiling point, density, hardness, solubility, and conductivity. So in this picture here, we have gold and fool's gold. And back in the day when they were digging up gold in, the early part moving out west in the United States, a lot of people thought that they had gold when really they had this pyrite. And they look similar, however, they do have different physical properties. So their densities are going to be different. The color is slightly different. Hardness will be different, as well as the melting point and boiling point. Physical changes happen when a substance is altered without changing the composition of that substance. So the inner elements and atoms aren't going to change, it's just going to change from either a solid to a liquid or a solid to a gas to a solid, a liquid to a solid, a liquid to a gas, or a gas to a liquid. Some other examples of physical change would be bending, crumpling, grinding or crushing, and cutting. So here in this example, it doesn't matter if you have a full sheet of paper or if you have it all torn up here, it's still going to be consisting of the same composition, which is that of paper. So a chemical property is going to be the ability or inability of a substance to combine with or change into one or more other substances. It's very different than the physical properties that we talked about because we were talking about those staying the same composition. Some examples of chemical properties include reactivity, flammability, toxicity, and acidity. Looking at this example here, we can see that iron and oxygen are going to react, and that's going to have this chemical property since it's reactive, and it would form this rust on your iron chain. With iron and nitrogen, so iron is not able to react with nitrogen. So if we have iron and nitrogen gas, those links will not react. So we can say that a chemical property of iron is that it reacts with oxygen. Another chemical property we can say is that it does not react with nitrogen. A chemical change is often referred to as a chemical reaction. When one or more substances change into new substances, a chemical change has occurred. Oftentimes, these changes will be irreversible. So if you're thinking in terms of a physical change, which you talked about last unit, we could go from liquid to gas to solid, and those kinds of changes were reversible. With a chemical change, most of the time you're not going to be able to get your starting material back. The ending substances will have completely different properties than the starting substances. And some terms that you might see included in a description of a chemical change would be produce, make, or create, decompose or rot, explode or burn, oxidize, corrode, tarnish or rust, or ferment. Those are just a handful of ones that you might see that would indicate that a chemical change has occurred. Some chemical changes that you might be familiar with would be when fruit oxidizes. So you can see that apple turned a yucky-ish brown color because it was exposed to oxygen. Another chemical change that is always occurring are going to be chemical changes in the body. Some specific ones would be in our digestive system. So we have to take that food energy and convert that energy through chemical changes so that our body can use it. Another chemical change would be the changing of leaves in the fall. And last, awesome chemical change that you might see in the summertime are going to be fireworks. So when you see a firework, there's actually a chemical change occurring. Now, in the lab, we can make observations and show evidence of chemical changes. So, the 5 main evidences of chemical changes that we would look for in a lab situation to see if a chemical reaction or a chemical change occurred would be energy change, odor change, precipitate formation, color change, and gas production. So, with energy change, oftentimes this means that you're going to observe a light given off by the reaction or a change in temperature. With odor change, obviously, you know what an odor is. So, this would be some sort of smell that is given off by the reaction. For example, an egg that has gone rotten is going to have a particular pretty nasty smell, and that is due to or in evidence that a chemical change occurred. Another one would be chocolate chip cookies. So the cookies don't smell as delicious when they are just raw cookie dough. However, when they are in the oven and they are cooking and baking, they're undergoing chemical change, and we can smell the change in composition of that cookie. Precipitate formation is when you have 2 aqueous solutions, and when they combine, they're going to form a solid precipitate. So a lot of times with this, you will see that this precipitate is going to be a cloudyish, opaque color in the solution, and a lot of times that precipitate will often be a little bit more dense than the solution and will go to the bottom of your test tube or your beaker and kind of settle, so you can see that there is that solid layer that was formed. Color change is another evidence of chemical change. So something you're probably familiar with is the Statue of Liberty. So at one time she was copper colored, and over time there was chemical reactions that occurred, and that copper reacted with the air and everything in the air around it, and it turned into this greenish copper carbonate greenish color that you're probably used to seeing. And the last is going to be gas production. So gas production, some observations that you might see in a lab are going to be that bubbles are forming, or gas is also present if you see fizzing as well. Now, it's good to note that gas production is a new substance being created. So by you boiling water, yes, you will see bubbles. However, you are not creating a new substance. That is just undergoing a phase change from the liquid form to the vapor form. A gas being produced is when you have a new substance that is being made. So we're going to learn a couple different ways of representing chemical reactions. For all of these chemical reactions, we're going to be talking about 2 main parts. So the reactants are going to be what you start with in the beginning of the reaction. So before the reaction takes place, you have reactants. And these are the things that are going to react. They're always going to be on the left side of the arrow. Products are going to be the substances that we have after the reaction occurs. So these are going to be what is produced. And these are always going to be on the right side of the arrow. Some common symbols that we will see are going to be the plus sign, which is going to separate different substances in the reactants or the products. So if I have more than one reactant, I would separate it with a plus sign, and that would show that I have 2 different substances. Same thing with the products. If I have more than one product, I'm going to use a plus sign to divide or to separate them out so that I can show that they're different substances. The arrow is going to represent the chemical change. You can also think of it saying yield, so the reactants yield products, or produce, so the reactants produce products. This arrow is going to be when the bonds are breaking, the atoms are rearranging, and new bonds are forming. And last, we will also see some little letters in parentheses that are going to represent the states of matter for a substance. So we have a little G for gas, a little S for solid, a little L for liquid. So that's talking about the pure liquid form. A lot of times we're going to be using water in its pure liquid form. But many times we're going to see that there are substances that are going to be dissolved in water, and that is going to be indicated by a little AQ to represent that it's an aqueous solution. So the first way that we can represent a chemical equation is through a word equation, and this is going to represent the chemical equation by using chemical names of the products and reactants. So here I just have a visual of a chemical reaction and the substances that are inside of it. And this is probably going to seem pretty familiar to you. So to begin with, I have sodium metal. So sodium metal looks like this. It's silver, it's shiny, it's soft, it's an alkali metal. Sodium reacts with chlorine gas, which I have here, which is going to be a greenish color. It's going to be gas at room temperature. And those are going to react together to form, right, or to produce table salt. So if I wanted to write this as a word equation, I would name my metal, so sodium. I would add it to chlorine, and then it would make sodium chloride. And you can see here that with those different names of the products and reactants, I made sure to put the states of matter. So sodium is a solid, chlorine is a gas, and then sodium chloride is also a solid. So a lot of times you might be given a description of a chemical reaction occurring, and you aren't going to specifically have it written out in a chemical reaction format or a chemical equation format. So you're going to have to decide, what are my reactants, what are my products, and you're going to put it into either a word equation or a chemical equation or formula equation. A chemical equation or a formula equation, or also known as a skeleton equation, is going to represent a chemical reaction through symbols and chemical formulas. So with this, we're basically taking that word equation and we're putting formulas to those different substances. So just a recall for formula writing and rules for elements and compounds. If you just have one single element or a pure element, generally you're just going to put the element symbol. So for example, if I have silver, I'm just going to write a G to represent my silver. The exception with pure elements are the diatomic elements. So if you remember, we had this discussion when we talked about molecules, and we also had this discussion when we talked about the periodic table. But there are certain elements that in nature are going to be bound to another atom of the same kind. So some of those different elements are going to include hydrogen, oxygen, so I'll just put a 2 here, nitrogen, and then the halogens. So we have fluorine, chlorine, bromine, and iodine. So I think in one of your lectures you had a mnemonic device that helped you remember which ones were diatomic. I just remember HON and then the halogens. When you're writing an ionic equation, remember to keep those charges in mind because the net charge has to be 0. So whenever you're thinking with ionic compounds, how to write the formulas, I know it's been a couple units since we did naming, you're going to remember that you have to think of what the charges are for your cation and for your anion. And those charges have to have a net charge of 0 in your compound. And then last is the covalent substances or covalent compounds. Remember that for these, you are using the prefixes to determine the number of atoms. So if I have mono or di or tri, etc., that's going to tell us how many of those atoms I have for that specific element in the covalent compound. So if I'm going to write a chemical equation for the word equation that we had for the last slide, I have sodium, which is a pure element, so I'm just going to write it Na. I'm just going to keep my little s there. And then chlorine. So remember that chlorine is one of those diatomic elements, and we're going to have to make sure that we write it as Cl2. And then those are going to react to form sodium chloride. Now, sodium chloride is an ionic compound. So when I'm writing the formula for ionics, remember that you want to think about the charges. So Na has a +1 charge, and chlorine or chloride has a -1 charge. Since these cancel out, I'm just going to write the formula as NaCl. And that is our skeleton or formula chemical equation. All right, so we're going to go through a couple examples of how to write these word and skeleton equations. So if I was given the description that aluminum reacts with chlorine gas to produce aluminum chloride, I would have to pick out what my reactants are and what my products are. So looking at the context clues in the description, it says that aluminum will react with chlorine gas. That tells me that aluminum and chlorine gas are going to be my reactants. And then it says that it produces aluminum chloride. So this would be my product. So when I write the word equation, I have aluminum, which is going to be a solid. It's going to react with chlorine, which is a gas. And those are going to produce aluminum chloride. And aluminum chloride is an ionic compound, so as you can recall, ionic compounds are generally going to be solids at room temperature. All right, so that is my word equation for this description. Now I'm going to write the skeleton equation or the formula equation. So aluminum, since it's just an element, is just going to be Al. Chlorine gas, again, is going to be Cl2 because it's a diatomic element. And then aluminum chloride, I got to think about the charges again. So we have aluminum that has a +3 charge and chlorine that has a -1 charge. I like to do the cross and drop method, or just think to yourself how many chlorines or chlorides would I need for every aluminum, and that would mean that my chemical formula for aluminum chloride is AlCl3. Remember. All right, another example. So it says a description of aluminum and oxygen are formed from the breakdown of aluminum oxide. So with this one, using my context clues, I can see that it says that aluminum and oxygen are formed. So that tells me that those are going to be present at the end of the chemical reaction, and these are actually going to be my products. And then it says that they're formed from the breakdown of aluminum oxide. So this is going to be what I start with in the reaction, which is going to be my reactant. So when I write the word, I'm going to write aluminum oxide. All right, aluminum oxide, again, is going to be an ionic compound, so I'm going to assume that it's going to be a solid. And then it says that's going to break down into aluminum, which is a solid, and oxygen. So notice that if I have two, I'm going to put that plus sign to show that they're different substances. And oxygen is going to be a gas at room temperature. So that is my word equation. Now from there, I'm going to make my skeleton or my formula equation. So aluminum oxide, again, as we said, was an ionic compound. So I'm thinking in terms of charges. So aluminum, remember, had a +3 charge, where oxygen has a -2 charge. So to make the formula, Al2O3. And then aluminum is a metal. It's a pure element just by itself. And oxygen is also one of those diatomic elements. So when I write the formula for oxygen, I have to make sure to put my subscript of 2. All right, so that is how we do word equations and skeleton equations. You'll notice that we had aluminum for the last reaction as a reactant, and in this reaction, it is a product. So it's really important to read some context and use context clues to figure out what your products and reactants are to write your formula equation correctly.